So today we're going to learn about absolute convergence and the ratio test. So I first need to define what absolute convergence means. So we say that a series, sigma as n goes from 1 to infinity of an, is called absolutely convergent if the series involving all of the absolute values of those terms converges. So for most of the series that we've been dealing with so far, those were already positive terms, in which case then if the series converged, it was automatically absolutely convergent because you take the absolute value of a positive term, it's still positive. However, we have recently talked about alternating series, and there's other possibilities where it's not strictly alternating, but there is a possible change in sign. And so in that case then, we are interested in whether if we ignored the positives and the negatives and strictly looked at positive terms, whether the series would be convergent or not. So that's called absolutely convergent. Now, you can imagine that there may be some series that won't converge if you only look at the absolute values of their terms and added those up, but might converge if you were allowed them to alternate or to have positives and negatives so that some of that would partially cancel out and you could get a convergent series. So we say that a series is conditionally convergent if when you look at the absolute value of those terms and add them up and do the series, you get a divergent series. But if you looked at the series itself, it would be convergent. So that's called conditionally convergent. So now we have two new definitions, absolutely convergent and conditionally convergent. So here's an example of one such series. So we did this series when we talked about the alternating series test in the last lesson. So this series, where you can see it's strictly alternating. If you look at the absolute value of the terms, you know that it's decreasing, that the an plus 1 term is less than the an term, because 1 over n plus 1 is less than 1 over n. So that's a decreasing series in the absolute sense. And if you do the limit of just the term itself, the limit of an, you would get 0. So, but the alternating series test, which we did last time, we did exactly this series, that series converges. However, if you do the absolute value of those terms and you made a new series, well, that would just be this series, the sigma of 1 over n. That's a harmonic series, or a p series with p equals 1, which diverges. So the series, the original series converges, but when you try to take the absolute value of the terms, that series diverges. So we say that the original series is conditionally convergent because it only converged because of that alternating. It wouldn't have converged in the absolute sense. So that's called a conditionally convergent series, and there's lots of them. Okay, here's another theorem which says that if a series absolutely converges, if you were able to take the sum of the absolute value of the terms and you get that to converge, then the series itself would converge. So this is a stronger convergence than the regular convergence. You can kind of see from the previous example that you can get an alternating series to converge, but that it might not absolutely converge. So you can sort of extrapolate that to say, well, if it absolutely converges, then if it's alternating, it'll be even easier to converge. So that's what the theorem says. I'm not going to go through the proof of it. But here's an example. I want to show that this series, sigma as n goes from 1 to infinity of cosine n over n squared, is convergent. So here's what we're going to do. We're going to consider sigma n equals 1 to infinity of absolute value of cosine n over n squared. Now, we know that 0 is less than or equal to absolute value of cosine n, which is less than or equal to 1 for all n in z plus. Which also means that 0 is less than or equal to absolute value of cosine n over n squared, which is less than or equal to 1 over n squared for all n in z plus. So I'm making a comparison test here for the series of absolute values. So if I look at the series of 1 over n squared, sigma as n goes from 1 to infinity of 1 over n squared, is a p-series p equals 2, which is greater than 1, so it converges. By the comparison test, sigma n equals 1 to infinity of absolute value of cosine n over n squared also converges. And by this theorem that I said over here, sigma as n goes from 1 to infinity of just cosine n over n squared also converges, because since the series was absolutely convergent, therefore it is convergent. So that's the clue, that's the key. If a series is absolutely convergent, then it is just regular convergent, old style convergent. Okay, so here's our next test. Actually, it's the last test we're going to have to learn as far as testing convergence of a series. So if you have a series, and we'll just call it sigma n goes from 1 to infinity of an, we are going to be able to test its absolute convergence using the ratio test. So what we do is we take the limit as n goes to infinity, and we just take two terms from that series, the an plus 1 term and the an term, and we do an plus 1 over an, and we do the absolute value of that. And if that limit is less than 1, then the series that we started with is going to be absolutely convergent. This absolute value is the key there, so it becomes absolutely convergent. I'm not going to be able to prove this to you. It's in the textbook, but I'm not going to stress over it. Okay, so if the limit of the absolute value of an plus 1 over an is less than 1, then this series is absolute convergent. Second possibility, if the limit as n goes to infinity of absolute value of an plus 1 over an, if we do that ratio and we get something greater than 1, then the series is divergent. However, if that same limit, absolute value of an plus 1 over an, is equal to 1, the ratio test is inconclusive. It's basically useless. So we'll have to find some other test. So that's what the ratio test does. It is sort of like comparison, except you're comparing to the same series itself, just two terms in that same series, the n plus 1 term and the n term. And there are certain types of series that sort of lend themselves to the ratio test, and we'll do some examples to illustrate it. So here we want to test the series sigma as n goes from 1 to infinity of negative 1 to the n times n cubed over 3 to the n. We want to test it for absolute convergence. Now, the clue that tells me that the ratio test is going to help is that I have some kind of a polynomial here, which is neither here nor there, and then I have an exponential. Now, if it was simply an exponential, I'd be in good shape. If it was simply a polynomial, I'd be in good shape. But this combination of the two types of functions that are kind of hard to mix and match means I'm going to try the ratio test. So here we go. Consider the limit as n goes to infinity of absolute value of an plus 1 over an, which is going to equal the limit as n goes to infinity of absolute value of, well, technically I'm going to put the negative 1 to the n part in there just to show it, but it's going to disappear because of the absolute value. Negative 1 to the n plus 1, n plus 1 cubed over 3 to the n plus 1. That was the an plus 1 term. Now I need to divide by the an term, which is literally just a copy of the one in the series. So negative 1 to the n cubed over 3 to the n. That's the an term. So I'm doing this this limit here. So what I'm going to do now is I'm going to, obviously the negative 1 to the n plus 1 disappears, and the negative 1 to the n disappears, and so I don't really need the absolute value after that because n is going to infinity. So it's the limit as n goes to infinity of, and so I'm going to take this bottom fraction and flip it upside down and multiply. So I'm going to have n plus 1 cubed over 3 to the n plus 1 times, now I'm going to get 3 to the n over n cubed. So that's the limit that I'm dealing with. So if I keep this going, that's going to equal the limit as n goes to infinity. So the 3 to the n and the 3 to the n plus 1 will partially cancel, so I'll be left with just a 3 on the bottom. So it's 3n cubed on the bottom and n plus 1 cubed on the top. Now I'm going to multiply the top and bottom by 1 over n cubed. I'm going to do that little trick. However, I'm going to realize that as soon as I try to insert this 1 over n cubed into this cube, that n, excuse me, that will turn into 1 over n. So each of these terms is divided by n, because when I cube it, that's how I get the n cubed. So it turns into n over n plus 1 over n quantity cubed over 3 n cubed over n cubed. Of course, you don't really need to write that step, but here we go. Limit as n approaches infinity of 1 plus 1 over n quantity cubed over 3. Now when you do that limit, you end up with 1 plus 0 and then cubed, which is 1, over 3. That's 1/3. Now notice that that is less than 1. And the ratio test says that if the ratio of these terms, an plus 1 over an in the absolute value sense, is less than 1, then this series absolutely converges. So by the ratio test, sigma n equals 1 to infinity, negative 1 to the n cubed over 3 to the n, whoops, 3 to the n, absolutely converges. And it's important to say that the result of the ratio test is that it absolutely converges, not just that it converges. Now you may only be asked in this particular problem to test convergence, but you still need to say that the ratio test result is that it absolutely converges. And in this case, that's what you wanted, so you're all set. Okay, here's another one that I want to do convergence on. Now similarly, what I have here is two different types of functions, so an exponential and a factorial. In fact, whenever there's a factorial, it tends to be that the ratio test is going to come into play, and you'll see why that happens in a second. So, I'm going to consider the limit as n approaches infinity of absolute value of an plus 1 over an. That's going to be the limit as n goes to infinity of absolute value of, well, it's going to be e to the n plus 1 over n plus 1 factorial. That's the an plus 1 term over e to the n over n factorial. That's the an term. And of course, the absolute value completely disappears here. There's no negative signs anyway, so you don't really need it. So I'm going to drop it. The limit as n goes to infinity, and now I'm going to recopy the numerator, e to the n plus 1 over n plus 1 factorial. And now I'm going to multiply by the reciprocal of the denominator fraction. So I'm going to have times n factorial over e to the n. Now I'm going to simplify that limit, and I'm going to get the limit as n goes to infinity. Well, one of the e to the n, sorry, the e to the n plus 1 of the e to the n would mostly cancel, with leaving me with just an e. And then when I do the factorials, n factorial will almost perfectly cancel with n plus 1 factorial, because n plus 1 factorial has all of n factorial times another n plus 1. So the only thing left will be my n plus 1 factor that was not in the n factorial. If you need an extra step, it's okay to write it this way, right? Because n factorial times n plus 1 is the n plus 1 factorial, and then cancel those out. I'm usually too lazy to do that, but it is an acceptable step if you want to show the extra step. So this becomes the limit as n goes to infinity of e over n plus 1. And as n goes to infinity, this turns to 0, which is less than 1, which is good. This means that by the ratio test, we showed that sigma n equals 1 to infinity of e to the n over n factorial absolutely converges, and therefore it converges. When we say absolutely converging, we are not trying to converges. Sorry, converges, yeah. When we say absolutely converges, we're not trying to emphasize that it converges. We're talking about the absolute values. So you also have to say that it therefore converges. Okay, so here's a slight variation on this problem. For what values of x is the sum from n, as n goes from 1 to infinity, of x minus 3 to the n over n convergent? Now, here, notice that n is the index. N is the number that is changing, and going from 1 to infinity, right? But x is some unknown. It's a variable inside there. It's not changing. It's not part of the changing index of the sum, but it is some variable in the problem. And I want to figure out for what values of x will I get this series to converge. So what I'm going to do is this. I'm going to consider the limit as n goes to infinity of absolute value of a sub n plus 1 over a sub n, which, if you don't want to write this specific thing and just start really over here with the terms written in the limit, that's okay. I just want to make it clear to everybody that I'm drawing the ratio test here. So it's going to be the limit as n goes to infinity of absolute value of, well, it's going to be x minus 3 to the n plus 1 over n plus 1. That's the n plus 1 term, divided by x minus 3 to the n over n. Now, I cannot get rid of the absolute values here because I don't know what x is. So it may make that negative, it may make that positive. I have no idea, so I have to leave the absolute value in these limits. So it's going to equal the limit as n approaches infinity of the absolute value of, I'm going to leave the x minus 3 to the n plus 1 and the n plus 1 alone, times, now I take the reciprocal of the bottom fraction, so n over x minus 3 to the n. Now when I start to pair things together, when I put this with this, I know that almost all of them cancel because there's n here and there's n plus 1 of them here. So I'm left with just absolute value of x minus 3. So I'm going to get the equal to limit as n goes to infinity of the absolute value of x minus 3. And then I do not manage to cancel n with n plus 1. So I pretty much just have to write times n over n plus 1. Now recall that x is an unknown. It has nothing to do with this limit. This limit is all about n goes to infinity. So let's focus on the n and just ignore the x for a second. If I want to simplify this limit or evaluate this limit, I need to multiply top and bottom by 1 over n. So I'm going to have limit as n goes to infinity of the absolute value of x minus 3 times 1 over 1 plus 1 over n. That's what I get when I multiply top and bottom by 1 over n. And so now it turns, as n goes to infinity, this becomes 0 here. So it's x minus 3, absolute value x minus 3 times 1 over 1. So just absolute value of x minus 3. Now the question asked, when is this series convergent? So the ratio test allows me to determine that this series is convergent if this result that I just got from the limit is less than 1. So let's see what happens when if that's the case. So I want to solve this inequality. Absolute value of x minus 3 is less than 1. Well, absolute value of x minus 3 would equal 1 if x was equal to either 2 or 4. So x is going to, in this case, be somewhere between 2 and 4. So this is the same as saying 2 less than x less than 4. However, this is true let me see, when 2 is less than x less than 4, the ratio test shows that sigma n equals 1 to infinity of x minus 3 to the n over n converges. However, remember that the ratio test is inconclusive if this limit is equal to 1. So I cannot make any conclusions about what happens when this is equal to 1. So I need to say that when absolute value of x minus 3 is equal to 1, which really means that x equals 2 or x equals 4, the ratio test is inconclusive. So I'm going to have to come up with some other method. So I'm going to have to go to the next page here to finish this off. So here we go. Here's the series again that we were considering. We know that when between x equals 2 and x equals 4, in other words, 2 less than x less than 4, we know the ratio test shows that it converged. But at 2 and 4, where the ratio test gave us a limit of 1, we don't know. So I need to test separately what happens when x equals 2 and what happens when x equals 4. So when x equals 2, we get sigma n equals 1 to infinity of x minus 3 to the n over n is going to equal sigma, as n goes from 1 to infinity, of 2 minus 3 to the n over n, which is basically sigma n equals 1 to infinity of negative 1 to the n over n. Now, I've actually done exactly this series before. This was the alternating harmonic series, which we know converges. It does not absolutely converge, but it converges. So the alternating harmonic series which converges. Now, when x equals 4, the series n equals 1 to infinity x minus 3 to the n over n is going to be the sum, as n goes from 1 to infinity, of 4 minus 3, which I'm just going to write as 1 to the n over n, which basically is just sigma of 1 over n. And this is the harmonic series, not the alternating harmonic, but the regular harmonic series, which diverges. So what I've discovered now, if I put it all together, the series that I started with, n equals 1 to infinity, x minus 3 to the n over n, is going to converge when 2 is less than or equal to x, which is less than 4. Because the 2 less than x less than 4 part came from the ratio test, and then by figuring out what happens at 2 and 4 using some other method, I figured out that x equals 2 is also part of the domain where the series converges, and so I have to include it. So this becomes my final answer for the question.